I'd say you can go ahead and get started.
Okay, all right, well, thank you. I wanted to say thank you for having me at the conference. This is my first time attending the AIPG conference, and my colleague Joyce Duncan, who's presenting on Thursday, had really got my enthusiasm up because of the beautiful setting that you usually have it at, which is at Higgins Lake. We were queued up to do this last year, but then COVID hit, and so we postponed for a year, and now I'm joining you from the beautiful confines of my office. So I don't think it's quite the same experience, but I am very appreciative to have the opportunity to talk to you about PFAS data management strategies, and to get to know some of you a little bit better through this conference. So with that, we'll get started here. So in terms of the talk that I'm going to give today, I just want to put a little structure around it. So here's a brief outline. I want to start with an introduction that provides background on PFAS. I assume most of you have already know something about it, but I just want to kind of set a level playing field for everyone that's attending, and then talk about sort of overarching data management strategy and considerations. And then I want to segue into the challenges and the fact that PFAS right now as sort of an area of interest has a lot of uncertainty, and I want to step through some of those uncertainties because they have implications on how we approach managing data from a project or from a site. And I've got sort of 5 areas that I want to talk through. One is just PFAS chemical categorization, analytical method developments, which our moderator Gail Carr can probably talk a lot about as well, regulatory criteria, the emerging remediation technologies, and then forensics and kind of future data application interests. So those are kind of areas of uncertainty that affect data management. And then, of course, we'll spend most of our time sort of talking about solutions and sort of focused around being careful and forward thinking given the uncertainties that I just mentioned, and efficient as well. So ultimately trying to suggest strategies that will help you keep what you need and disregard what you don't need. Of course, that will vary from site to site. Keep what really matters given these uncertainties. Kind of figure out what to do with all that laboratory QA/QC data, and sort of figure out, do we really need to hire a chemist to make sense of this data? So I'm going to try to make some suggestions that will hopefully help you answer some of these questions and give you some ideas for what to do with data from your sites or your project areas. So let's start first with the introduction. This will be a little bit of background on PFAS and the need for good data management. And I'm having just a little visualization issue, so I'm going to make an adjustment here. Okay, so what is PFAS? What are PFAS? So PFAS stands for per and polyfluoroalkyl alkyl substances. These are a type of organic compound that are man-made, generally contain at least 4 carbon atoms. The figures on the right show a couple of examples. The black balls are carbon atoms. The green balls are fluorine atoms. So these are compounds that have that carbon-fluorine bond associated with them, usually in a chain, and then there's a functional group at one end. And usually it's a sulfonate group or carboxylic acid. What I'm showing on the right-hand side here, that top structure is PFOS, which is an 8-chain carbon with a sulfate group at the end. And then the bottom compound is PFOA, which is a carboxylic acid with 2 oxygens and a hydrogen as the functional group. That carbon fluorine bond that you see that dominates the chain, the carbon chain, that's a really strong bond. It's one of the strongest in nature. So it makes these compounds extremely stable, and we'll talk about the implications for that when we move on to chemical properties in just a few slides. But but it's a really, really useful chemical because of that bond and that functional group that you can attach to the end, and makes it very versatile and used a lot in a lot of different applications, which I'll talk about shortly. In addition to kind of these are perfluorinated alkyl substance examples, but there are other compounds that sort of fall into this category that are called precursors. And I've got a list here: sulfonamides, fluorotelomere sulfonates, FTSs, FTOHs, which are fluorotelomere alcohols, and really the basic difference in these precursors has to do with the functional group, kind of the head of the molecule, and the type of fluorine substitution. So I've got kind of the chemical formula in a very generic nature for these precursors kind of shown at the bottom. So there's lots of different ways to manipulate these types of compounds to produce thousands of potential compounds that would be considered PFAS or PFAS chemicals. So in terms of environmental concerns, I talked about that stability, the strength of that carbon-fluorine bond, and in combination with that functional group at the head of the molecule, that gives these compounds some unique physical chemical properties. Probably the most important is that it is both hydrophobic and hydrophilic. That carbon-fluorine bond does not like to be in water, so it's hydrophobic. It's repelled. But then that functional group is usually very water soluble, so that gives it hydrophilic properties as well. So that contributes to its versatility. In general, it's not very volatile. That has implications when it comes to treatment technologies. Because of that bond strength, it's resistant to degradation, and it sticks around in the environment. Once it's released, it tends to stick around. So that presents challenges in terms of remediating, and then of course that leads to the adverse effects that have raised environmental concerns, including the fact that it will bioaccumulate in fish and wildlife, and has been linked to human health impacts related to liver, thyroid, fertility issues, cancers, and a lot of that environmental impact or toxicity studies are currently being actively studied. So I mentioned the versatility of this chemical class. We see it in a lot of different areas. Some of the most common are shown here. It's used as a firefighting material, aqueous film-forming foam, which is used at airports a lot. Chrome plating, it's a way to used in demisters or misting agents for chrome plating operations. Paper mills and other industries use these types of compounds a lot. So there's obviously a lot of industrial applications, but then those lead to their pervasiveness in household products. It's in clothing, Gore-Tex, food packaging. It's why your hamburger wrapper, the grease doesn't go through, or pizza boxes, carpet. It's ubiquitous in our everyday life, and so that presents challenges in terms of sampling as well as remediation and treatment. So that's kind of an overview, high level on PFAS. What I want to talk about next is data management strategy, and the way I want to talk about that is really in the context of what's called the DIKW pyramid, which is really a way to sort of structure how we move from data to decisions. And what we first collect at a site, and the subject of this talk is really about managing data, which is the bottom level of this pyramid. And once we have that data and we put some context around it through either the data management strategy or other types of activities, then we start moving up this pyramid, and we go from just having information about the signal to more structured context and knowledge, and then wisdom, which allows us to make good decisions. So as we move up this pyramid, we're adding value to the initial data. And What we're really talking about here today, what I'm trying to talk about is trying to manage the data at that lowest rung on the pyramid so that we can facilitate the movement up this knowledge pyramid to a place that allows us to make good decisions based on the data. So I'm going to probably come back to this reference a few times through the talk, but hopefully this is something that is familiar, or at least if it's new, it makes sense to you. Okay, so the next kind of section of my talk, I want to talk about some of the challenges that we're facing with PFAS currently, and all of these have implications for data and data management. So at the outset of the talk, I mentioned 5 areas, so let's talk about those. And I've got them summarized here, but we'll go into each of these sort of one by one. So some of the hazards of PFAS data management are listed here. You know, the analytical methods are evolving. I'll talk about some elements of that. As we learn more about PFAS and develop our expertise, we're having an increasing ability to look at differences in chemical properties and different types of PFAS compounds. The regulatory field is pretty decentralized right now. Things are happening at state level more so than at the federal level, so that's causing potentially confusion or different challenges depending on what state you're in. And then we're kind of seeing a race to the bottom in terms of regulatory criteria. So that's really pushing analytical detection limits and you know, kind of making it a challenge to understand sort of where you fall, where your site conditions fall with respect to these super low criteria that can be difficult to meet with current analytical technology. And then remediation technologies are still being developed. There's some ones that are used more frequently that I'll talk about, but there's a lot that are currently being researched. And then the future applications, there are some that have been identified but not fully developed that, as they come down the pike, could affect how we look at PFAS and how we collect data and how we manage it. And those include, you know, kind of a broader regulatory strategy that I'll talk about, as well as kind of interest in forensics and trying to apply the data in a way that provides more information about sources of the release and timing of the release. So we'll go through each of these kind of one by one here in the next couple slides. So first up, the analytical methods are still being developed. So EPA has really only approved analytical methods for drinking water. Their first one came out in 2009, and they updated that just a couple of years ago to method 537.1, and then a year after that added method 533. So 537.1 is sort of the classic set of perfluorinated alkyl substances. 533 adds some shorter chain and what are called Gen X compounds, or more recent chemicals that were developed to replace the perfluorinated alkyl substance versions of these compounds. In addition, ASTM has methods that they've developed for soils and non-potable water. You know, in my experience, those have traditionally been viewed and used as screening methods, but you know, not always. And you know, there have been additional developments in those methods that have made them more robust as well. So so what we've seen over the last few years is that a lot of laboratories are using what's called method 537M or 537 modified, and use that as a catch-all for deviations from the EPA approved method. So they'll use 537M if they're, you know, applying, if they're analyzing for different media, soil or water, surface water, groundwater. If the sample preservation or volume has changed, if the analysis or prep methods are different than what's prescribed in the EPA methods, if the quantitation method is different, if the analyte list is different, if we're using different QA/QC measures, anything that departs from method 537.1 would now probably be tagged with the 537M. And so each lab sort of develops their own SOPs for how to do that. So how to do their own methods. So there can be some variability in what constitutes a 537M result from one lab to another. So that that can cause some challenges in terms of comparability. Just adding to the analytical methods still being developed, there's a lot of work being done here, and this is a very dynamic part of the PFAS arena. So, you know, analytes are being added. We're developing additional standards and additional capabilities. So, for example, EPA, the first EPA method was set up for 14 compounds. The latest method is 18 compounds. States are developing their own list based on the evolution of technology. So Michigan, for example, has been using 24 compounds as kind of their standard list. Wisconsin was using 36. And you know what we're seeing in some of our discussions with laboratories now is that there's enough, the technology and standards have evolved to the point where, you know, upwards of 50 compounds could potentially be quantified now. So that's a really dynamic area that that I expect will continue to develop. There are many PFAS for which standards don't exist, so they can't really be effectively quantitated, but they could be identified as present in your sample. And that's another aspect of an analysis that goes in, you know, could be part of your sampling plan. And, you know, some labs are reporting, you know, over 2,000, 2,400 analytes can be qualitatively identified this way without quantitation, but, you know, kind of a presence absence type of result. So, you know, analyte lists are a big area of development and an important part of setting up your data management strategy. Quantitation method is also a really important part of analytical methods. There's kind of three main techniques that are used: external standard quantitation, which is what the ASTM methods use; internal standard quantitation, which was what the original EPA 537 method used, very similar to, you know, traditional 8260 or 8270 type of quantitation. And then probably the most accurate and kind of the gold standard is isotope dilution quantitation. That's what I think most labs are using when they use 537M. EPA 533 method uses this quantitation. And then the Department of Defense QSM 5.3 has a table of QC requirements that include isotope dilution. So this is really the ultimate method of quantitating PFAS compounds, and is used by many labs. But there are also non-specific methods. Probably the most familiar or commonly discussed one is the TOP assay, or total oxidizable precursor assay. So what this does is it's a kind of a digestion, I'll call it a digestion step, but it basically takes your precursors and converts them to perfluorinated end products that then you can measure with a traditional PFAS analysis. So you can measure your analyte list initially, and then run a top procedure on it and remeasure it, and it tells you a little bit about what your potential risk could be if all those oxidizable precursors eventually make their way, degrade into perfluorinated end products. PIG-E is another one that I see a lot, and this measures total organofluorine concentration using gamma ray technology. So there's a lot of movement on analytical methods. And then that kind of feeds into some of the chemical property and structure uncertainties. So just kind of very broadly, there's really no consensus on what chemicals should be included in the PFAS family. You know, right now we're dealing with a relatively small number of analytes, although that list, as I just said, is expanding, but it does raise questions about what analytes should be included. And as I'll talk about in a minute, you know, different states are developing their own regulations. So key analytes from state to state are different based on kind of what the regulatory environment is in that state. So that's one element of the chemical properties that is an uncertainty. And then the next one is dealing with isomers. So we've got these kind of long large chemicals. And isomers are basically, they have compounds that have the same chemical formula but have different structures. So I've got an example here where we're showing on the left-hand side linear version of PFOA. I showed that earlier, where it's just kind of a straight chain carbon fluorine chain with the carboxylic acid group on the end. But you can move those carbon fluorine bonds around and create these kind of branched versions, which I'm showing on the right-hand side, where you've got, instead of a straight chain, you've got these kind of two-side small chains feeding into kind of the longer part of the chain and then into the carboxylic acid functional group. And so these have different chemical properties and environmental impacts. So the question is, do we report these together? Do we report them separately? The chromatogram on the right is kind of an example that from Test America that shows that it's possible to separate these, but then what do you do in terms of quantitation? Good news is that, we're now seeing more linear branch standards available, so we can quantitate them separately. But, what we need is a data management strategy that can reflect these advancements of analytical methods and the thinking on PFAS as a whole, so that we can, make comparisons of different data sets from different time periods from different laboratories. So it's not a straightforward process, but it's definitely something that we need to consider as we start thinking about a data management strategy. In terms of regulatory criteria, there is no federal criteria. There's a federal health advisory guideline for PFOS and PFOA that's 70 nanograms per liter individually or as a sum of both. It's not promulgated, so it's not an enforceable standard. So states are developing their own criteria for drinking water as well as other media, soil cleanup standards, groundwater, surface water. States often have, the state criteria is often lower than the federal guidance value. So just an example, I've got Michigan's drinking water MCLs shown in that table on the right. PFOA and PFOS are the first two listed. So the EPA is using 70 nanograms per liter as individually as a sum of both, but Michigan's regulating those at 8 and 16 nanograms per liter, respectively. The states are also pushing analytical detection limits. I mentioned that earlier. The graph on the right kind of shows for PFNA a typical quantitation range of 0 to 200. Michigan's MCL is down here at 6 nanograms per liter. And the reporting limit from the laboratory that we were working with at the time is 3.7 nanograms per liter. So the criteria is very close to the reporting limit. So that can be a really challenging in terms of interpreting the data. And then the states are expanding their list of PFAS analytes beyond PFOS and PFOA. The table on the right here that I'm showing for Michigan shows that, they've got 6-7 compounds that they're regulating. Other states have more or less. So as more information is gained about the toxicity and health impacts and environmental impacts of these compounds, states are stepping up to regulate more and more of them. The other aspect of regulatory criteria that I wanted to touch on is that there's been some discussion about what basis should we be using to regulate PFAS, and there's a couple that are being sort of bandied about, and I just wanted to mention these briefly. What we're seeing most often is compound specific, right? You identify a safe concentration by individual compound, and you set your standard accordingly. That's what the Michigan MCLs are an example of that. Kind of a twist on that is to do an additive regulatory strategy where you develop a single value that is applied to the sum of the individual compound concentrations. So, 70 nanograms per liter as the sum of PFOS and PFOA would be an example of that. Subclass where it's another kind of potential regulatory strategy where compounds are grouped based on their physicochemical properties. That could be based on, we group all the carboxylic acids together and all the sulfonates together and regulate them as classes on that basis. And then TEQ based, that's TEQ stands for toxicity equivalent quotient. This is allows us to sort of rank or use the relative potency of the toxicity of each individual compound, kind of characterize that relative to the most toxic member. This is very similar to what how dibenzodioxins have been evaluated, where TEQs were developed for everything relative to TCDD, the most toxic member. So this kind of approach allows differences between compounds to be weighted based on their relative risk, and that obviously is not unprecedented because of the dioxin example. And then the last kind of basis is just to regulate them as a class, and just use some sort of non-targeted analytical method that measures some distinct characteristic, like organofluorine, and use that as the basis for regulation. In terms of, one of the reasons why I bring this up is that, we always strive for defensible data, but, it seems even more so that is important in a period of regulatory uncertainty, and sort of trying to anticipate where EPA or states might move in terms of regulating PFAS. Mitigation and remediation technologies. I talked about the stability of these compounds, so that makes it really challenging to destroy them. And the methods to destroy them are energy intensive. Incineration is an example, but typically it takes higher temperatures to get that complete destruction. Electrooxidation and sonication are a couple other methods that can destroy PFAS. I don't see those commercially applied. I think they're still mostly under development. The two kind of technologies that I do see a lot are granular activated carbon and ion exchange. These serve to remove PFAS from one media, which is usually water, and then put it in another media, such as the carbon or the resin. So it doesn't destroy them, but it does remove them from the media, the critical media, like drinking water. But they have variable effectiveness. So studies have shown that activated carbon works well for longer chain PFAS compounds. Ion exchange tends to maybe work a little bit better for some of the shorter chain PFAS compounds. There's also a host of new methods that are currently being researched by CERDIP and WRF and other research organizations, and there's kind of a list there. I confess I don't really know a lot about these in detail, but just know that there's a lot of research on this front currently being undertaken. But what's important is to know that we need to understand sort of what these kind of technologies need in terms of information, so that we can kind of capture those needs in our data management strategy. Okay, and then the last area I want to talk about of uncertainty is forensics. This is kind of a simple idea that's been used for other chemical classes, which is to kind of compare compound distribution between sources. And the benefit of this, and the example below shows kind of what the compound distribution looks like from groundwater that is impacted by AFFF firefighting foam versus what the compound distribution looks like for a couple samples on the right-hand graph, which those have been impacted by releases from a landfill. And you can see that the compound pattern is different. So this has the potential to be a really valuable tool in identifying the origins of PFAS in the environment, and being able to determine even potentially the vintage of the original product. Firefighting foams, their formulations have evolved over time. Originally it was predominantly PFOS, had a much larger fraction of those foams in earlier formulations and in later formulations. So we can look at how these compound distributions might tell us something about that. And so, we need to plan for the development of these these techniques as we plan our data management strategy and try to anticipate that this is an area of interest. There's lots of debates about splitting versus lumping compounds for assessing source materials. So how do we try to accommodate that in the data management strategy? So those are the areas of uncertainty. I'm going to move now to talk about data management and potential solutions and suggestions. You know, at LimnoTech, which is where I work, you know, we tend to work on sites with complex problems and long timelines. So that means that we often see data from multiple labs and multiple contractors, and you know, even different site owners at the same site can change. So you know, the strategies I'm going to suggest here have really come out of my over 20-year career working on sites contaminated, you know, with typical legacy pollutants, you know, PCBs, dioxins, PAHs, and now moving to PFASs. You know, I've been able to reuse many of those same strategies, but I've also identified some uniqueness about PFAS data that I also wanted to present here. So, you know, in my mind, the key to effective data management is balancing the information needs with the level of effort. You know, we can try to capture every last detail in a data management framework, and you know, and in some cases that's entirely appropriate, but you know, that can take a lot of effort and maybe beyond the project resources to support. So what I'm going to recommend in these next few slides, you know, really tries to strike a balance between what I think is important in a very general sense versus, you know, what the project resources may be able to support, and recognizing that, you know, you may need to scale up or down your data management efforts as the project demands. But there's really kind of three key things that I want to consider in an effective data management strategy. First is ensuring that we can have comparability between data sets, given that, you know, there are uncertainties and differences in methods and different analyte lists, et cetera, as well as differences in regulatory standards. I also want to make sure that false positives are able to be called out and identified as part of a data management strategy. And then also, you know, trying to the extent that we can sort of anticipate how we might want to use the data in the future and try to plan for that. And, you know, that's tough to anticipate, but we already know where the areas of interest are just based on where the research is going. So trying to plan for that is another element of effective data management. So I'm going to suggest that relational databases are a great way to sort of frame your data management. I recommend this for any data management effort, not just PFAS. It's a great way to meld field information with critical lab information. And so, for example, in this slide, you know, our database structure consists of different tables that are related by shared inputs. So the field information is contained in the station and samples table, and the analytical information is contained in the results and parameters. The value of these relational databases are that you know, they can be a centralized repository. They enforce a standardized data format, which can avoid confusion if you're in a multi-year project. It enforces you to make decisions upfront about things like, you know, is station MW01 at the same location as MW1 in this other data set? So you confront those things at the outset, and that just can save a lot of time and energy on the back end. And that's called, you know, kind of referential integrity. So that imposes consistency and fosters efficiency. So, you know, what I'm showing here is kind of a relatively simple structure, but it hits on a lot of the key elements that we want to retain from the field and lab effort. You know, I know that, you know, some site requirements will necessitate a more detailed structure where, you know, you may want to maintain all of the lab supplied information and, you know, have many more fields for notations on the field effort. The important thing is that these relational databases can be right-sized for your site and your project, even when there's a lot of unknowns, and they're flexible so you can expand in the future as you need. So what I suggest to include with the data, this is an example where, you know, the chemical and risk characteristics, which are some of the static information that I've listed on the left-hand side of this graph, for PFAS data, it's much more extensive than what I've tended to compile for other contaminants. And a lot of this is just driven by the uncertainties that I've mentioned, and just not being sure what we're going to want or need down the road to ensure comparability and defensibility. But some of the key static information, and I'll show an example of this. I like to embed the compound characteristics, not just the name of the compound, but the functional group, the carbon count, the longest carbon chain length, whether it's a per or polyfluoroalkyl compound versus a Gen X compound, what the isomer structure is, if there's a TEQ value. All of these compound characteristics are static. Something like the TEQ may change, but in general, that'll be a relatively stable input that you won't need to update very often. The chemical abstract number is another thing that I like to embed in there, but recognize that some labs use the CAS number for the acid, some use it for the salt. So it's something that we just have to be aware of and reconcile. And then, a lot of times we're interested in looking at total PFAS, and what does that mean when you have analyte lists that are constantly changing, or you have branched and linear isomers reported separately as well as a total? How do you avoid double counting? How do you make sure that your total from an analyte list of 36 compounds can be compared to a total of a result based on 14 compounds? So our strategy has been to kind of compile a short list that really is just the key perfluorinated compounds only. And we've got kind of what I'll call our medium list, which is consistent over time. And then we've got a long list, which is based on the regulatory drivers of the given site. So again, that's fairly static. It may change, but in general, we wouldn't expect to update that very often because we do want that comparability over time. And then on the right-hand side is sample-specific information. This is really common. A lot of this is common stuff that you do, even if it was something besides PFAS. So, logging the sample media. We have very specific media categories that we like to use. And then when we get to sediment, we like to characterize it as surface versus depth, because that has implications for some of the decisions that we're going to make. Sample depth, analytical method, those are kind of standard sample information that you want to store. But when it comes to PFAS, I think it's really important to store the quantitation method, the MDL, PQL, and RL because of the regulatory requirements, the laboratory, and then as well as the sample ID, both the field sample ID and the lab sample ID, because there may be need, and there often is, to be able to trace back a result from the result to the lab sample ID to the field sample ID to the site. So capturing all of that in your data management framework up front is really time well spent in my opinion. So here's an example of our parameter table in our database, and this is where we've embedded a lot of the static information. We've got parameter name and parameter ID, which you might think, that's kind of silly, but it seems simple, but it's actually one of the most challenging things is consistent analyte naming. Some labs use the full IUPAC name, some use a shortened name, some just use the abbreviation. So standardizing the naming convention and being able to translate the lab reports to a consistent name is actually a pretty common thing that you'll need to do. But you can see here, hopefully you can see this, it's not too small on your screen, but we've got a field for the carbon count, the carbon chain length, if it's a member of our standard 24 analytes, what the functional group is, and then what to include if we want to calculate a total using our short list, medium list, or long list. And then here's what it looks like in practice. Just show the PFOA. We've got PFOA reported as a total, and then we've got separate fields to track, results that are reported as linear versus branched. And then when it comes to totaling them, we only use the one analyte, and we want to try to ensure that we're not double counting. And then another kind of important element here is what to do with all these lab qualifiers. The labs that we work with are really, really good at documenting deviations from their individual 537M method requirements. And so the challenge is determining the significance of each of those deviations on the overall decision-making process as you move up that DIKY pyramid. So that's what this first bullet is really about. How do we sift through these qualifiers and assess significance for the decisions that we need to make as site managers or project engineers? And so, there's lots of lab qualifiers. There's a simpler set of validation qualifiers that, kind of boil down to these four. For PFAS, what has worked well for me is to kind of use the validation qualifiers as a starting point and then expand those to facilitate data interpretation. So, for example, we've expanded the J flag to indicate whether the estimated value is potentially biased high or low. We've expanded the B flag to distinguish between field and lab link contamination. We've added flags for greater than and then dilution, D for dilution, if the reported value is based on a diluted sample, because that has implications for the associated QA/QC. And then a lot of times we keep the lab qualifiers in a separate field just for reference in case we do need to go back. The challenge with that is that different labs use different qualifiers for with the same meaning, so we have to have a kind of a standardized set. So sometimes there's an additional translation step required there. And what we really want to do is get to final data. I always tried to only put final data in the data management system. It's better to put complete data sets than partial. It's hard to go back and backfill. And then we always try to document the effort via data entry log or table in the database where we track the who, what, where, when elements of adding the data to the database. We do a very thorough review of the data before we put it in, because we do want to try to identify false positives and understand all of that laboratory QC and how that might affect flagging as a result as having a potential bias. I do recommend that you can avoid confusion and inconsistency by if you have someone with a strong chemistry background. They don't have to be a chemist, but if they had a strong chemistry background, kind of looking at the data, because there is a lot to digest there. And then putting the data in context. I mean, this is sort of standard operating procedures, but pulling the data back to the field and site information through mapping or looking at vertical profiles and looking at data compared to previous results. So those are some of my strategies that I recommend in terms of key takeaways. I talked about the uncertainty around various elements of PFAS classes, analytical methods, regulatory standards, remediation. All of those complicate data management. There's a well-structured data management system can be set up to sort of address these uncertainties and minimize unnecessary work. And the right data management structure can be flexible so that you can adapt it as you need to customize for your specific project needs and future changes that might be needed. So that wraps it up. I would be happy to take any questions. I have not been paying attention to the chat. I'm gonna. Gail, is it all right if I stop sharing my screen so I can?
Yeah, you can. Yeah.
Everybody.
And I don't see any questions in the chat box, but if anybody has any questions and want to raise their hand or unmute themselves and ask Carrie directly, that would be fine.
Oh, great question from Brian. I see popped up. What is your preferred software for a relational database? It depends on the site and the level of effort of investigation. Here at LimnoTech, we've tended to use just Microsoft Access. As versions of Office have evolved, it's more robust and it interfaces well with Excel. We do a lot of sort of VBA programming to facilitate data transfer and data analysis, and exporting to more sophisticated analysis in R and Python. But we've also used SQL platforms for really complex sites, and a lot of times that decision is also based on who else is working on the site, and kind of working together to develop sort of a consensus around what works best. So that's my experience, and happy to hear what others on this call might have as well in their experience. Oh, but everybody's muted, so I guess,
Yeah,
it's just me.
I think you can unmute yourself, or if you should be a hand or something here, I can unmute you as well. Any other questions? Not seeing anything. If not, Carrie, thank you very much. We appreciate it. Great talk. And hopefully we'll get to see you in person next year.
Yeah, I hope so. Yeah, this is great. I love this group. This takes me back to my lab days as well. And yeah, I appreciate everybody attending and your interest. And I think Sarah's going to distribute copies of the presentations or make them available. So my contact information is on the slide, but also feel free to reach out through the Vahova app as well. So thanks.
Okay. Thanks, everyone. Thanks for joining us.